Now the next section we're going to be looking at are inclined planes. And so to start with this, we want to start by looking at the normal force and the gravitational force. Now we've already looked at those on flat surfaces. And so remember that if you have an object that's sitting on a flat surface, it just stays there on that surface. So unless you put some horizontal force on it, of course. But if you just place it down on a flat surface, it's not going to move. And the reason it doesn't move is because the force normal and the force of gravity are equal and opposite. So if I have a flat surface here, and then we just look at the rules for force normal and force of gravity. Force of gravity is always pulling straight down, and so that'll be there. Now force normal is always perpendicular to the surface, and on a flat surface, that's going to then be straight up. And so because my force normal is straight up, my force of gravity is straight down, those then are going to be balanced, and so there's nothing basically trying to move this, or there's no force that's going to try to propel this in one direction or the other. And so those ones stay balanced. Now if I put an object on an inclined plane, and we'll start with something that's frictionless, so it's really just gravity and normal force that's acting on it, what we're going to get is we're going to get a net downward force there. Now that's because the normal force changes. So my force of gravity is still going to be straight down. My force normal though is perpendicular to the surface. So if it's perpendicular to the surface, that's going to be heading along this path. And the steeper the ramp, the more offset that's going to be. So on a flat plane, those two are equal and opposite because they're along the same plane. As soon as I start tilting that ramp up, my force of gravity stays in the same orientation, but my force normal, which is perpendicular to the surface, basically starts pointing a little bit further down. And so they're not aligned anymore, and we're actually going to get a net basically pull down the ramp. And so I'll always get a net force whenever I'm on a ramp because this force normal and force of gravity won't be aligned. And again, the greater the angle of inclination, and so this is the angle you'll typically be given, the angle from the basically horizontal. The greater that angle, the less aligned those are going to be, and the greater than the net force we're going to have acting down that ramp. Now, if I want to find this net force that's pulling down the ramp, I'll need to combine my force normal and my force of gravity. And the net force, of course, will be the vector sum of those two. Now, these two vectors aren't aligned along a single plane, so that means I'm going to have to draw these two head to tail and then use the vector sum to come up with what that force net is. So I've drawn the arrows in on this diagram here, on a bigger diagram to give us a little bit more space. And so what we see here is we have the force normal, which is this red line heading up. We have my force of gravity, which is this green line heading down, and then I have my net force then over here. And so the first thing we need to recognize is that we're looking for a vector sum of this force normal and the force of gravity, because those are my two real vectors, and then the force net is just the sum of those two. So I'm just going to select this one here, and I'm going to move this down here, basically so that they're head to tail. So remember with your net force diagrams, we tend to draw all the forces out from the same point, but when I'm adding vectors, I need to add them head to tail. So I have my normal force here, starting here and then heading up, and then where that one ends, I draw my force of gravity. Now those are my two real forces. Now the sum of those, where I started to where I finished, must be then my net force. So what I can do is I can redraw this basically as a vector triangle. And so when I redraw those, I have my force normal acting over here. The one in blue will be then my force net. And then the one in green will be, of course, my force of gravity. And again, remember how these go. The two real vectors that I'm adding up together, those are drawn head to tail. And then my net force vector is where the sum started to where it ended up. Now the other thing that might not be obvious, but we'll get to that in a minute, is that this angle up here is also equal then to the angle of the incline. So we'll come back to that in a moment and we'll kind of show that that's true. But for a moment, just take my word for that. This angle in the triangle here is this angle there. Now my force normal, which is acting perpendicular to the surface, must be perpendicular to the force net because the force net is the motion of the box, which is along the surface. And so we can see that this is a right angle triangle, and this force of gravity then is the hypotenuse for that right angle triangle. So what I'm going to be interested in is what is this force normal and what is this force net. So we'll start with the force normal. Now this force normal is on the adjacent side to this angle. Force of gravity is my hypotenuse, and so for this one here I'll use cosine for that. So I have cosine of the angle, and remember that's the angle of inclination. We'll come back to why that is in a moment. That's going to be equal to then that force normal over my force of gravity, which means that the force normal for any inclined plane problem will be then the force of gravity times cos theta, or force normal equals mg cos theta. And that's something that's going to be worth memorizing because you'll get a lot of ramp questions. And anytime you're on a ramp or inclined plane and you're looking for the force normal, it's going to be mg times cosine of the angle of inclination. So not on your formula sheet, and you could just derive this each time, but it's going to be much quicker just to have that one memorized. So force normal equals mg cos theta. That'll be the normal force for anything on a ramp. It does actually come from just this vector triangle. Now the other one we're going to look at here is this force net. Now this is not necessarily what we want to refer to as force net because we don't have other forces here. So I could be, for instance, pulling on this with some applied force. I could be pushing it up or down the ramp. I could have forces of friction. So there are other forces I could put in here as well, which would add then to the total force net. What we're looking at with this force net, and it is a net force, is just though the sum of the force normal and the force of gravity. And it turns out that that's a sum we want to use quite a bit. So what we're actually going to do is we're going to rename that one force parallel. Now again, it's not a real force acting on the mass. It's the sum, though, of the normal and gravitational forces. And so we'll call that force parallel, and we can derive that from a triangle as well, because this one now is on the opposite side. So if I take the sine of the angle, that'll be equal then to that force net, which we'll now call force parallel, and then over top of force of gravity, which is, of course, the hypotenuse. And so then my force of gravity times sine theta is equal now to this force parallel, which is then the sum of the force normal and force of gravity. And so mg sine theta is equal to that force parallel. Now this is another one that's going to come up a lot, and so I'd highly recommend just memorizing that one. Force parallel, which is the net force, summing up the force of gravity and the force normal, and then force normal on a ramp, which is that one there. Now we didn't look at kind of why those two angles were the same, so we can do that for a moment. Now again, if you just memorize these equations, you won't have to derive this each time, but if you are interested into how those two relate, what we'll look at is my force of gravity is going straight down. And if my force of gravity is straight down, that means this is a right angle. And if this is a right angle, the sum of the angles in the triangle have to be 180. So 180 minus 90 is 90, and then minus this. So that means that this angle up here is going to be 90 minus this angle theta, so whatever this one is. So this one's 90, 90 minus theta, and theta. And that'll give you then a sum of 180. It's also true, however, that this force normal here must be perpendicular to the surface. And if that's perpendicular to the surface, then this whole angle here must be a 90-degree angle, going from the surface all the way to there. Now that right now is split up into two, 90 minus theta and theta. And so if I want to know what this angle is over here, I can take 90, which is this whole angle over here, minus just this component to the angle, which is 90 minus theta. Now 90 minus 90 is 0, minus and minus gives me positive theta. And so we can show that this angle, which is the inclination angle, and that's always going to be the angle given in the question, is equal to this angle in the triangle, which we were then able to use to relate the force normal to the force of gravity, giving us mg cos theta, and then the net force from the sum of the force normal and force of gravity to this now new force parallel being mg sine theta. Now there is a reason why we might want to introduce then a somewhat imaginary force into our diagrams, because what it allows us to do is to take a two-dimensional problem and solve it as a one-dimensional problem. So let's look at something like this box here, and if we draw the free body diagram for one which involves friction. So I get my normal force heading up like this, I'll have my gravitational force heading down like this, and then I'll put a friction force sliding down the ramp, so I'll put a friction force going backwards. And then we have then a net force going down. And so that's going to give us a fairly complicated vector diagram at the end of the day. My net force. That'll give me a fairly complicated vector diagram once all the forces are in. Now I can simplify that with the force parallel, because the only two vectors that are kind of off here are my force normal and my force of gravity. My net force and my friction force are along the same plane, and my force parallel is along that same plane. So this is my free body diagram. If you're asked for the free body diagram, the three real forces acting on it are force normal, force of gravity, and force of friction. Those are the real forces acting on it. And those would sum up then to what this net force is. What we're going to do is we're going to redraw the force normal and force of gravity as my force parallel. And so if I have a force parallel, which is along the surface of the ramp here, that replaces my force normal and my force of gravity. Now I can still add in my force of friction, but now what we see is that my force of friction is in the same plane. And so what I now have is I have a one-dimensional problem. And my net force is still going to be, say, down the ramp, but now my force net, my force parallel, and my force of friction, all of these are in the same plane. So these are equivalent diagrams. Now this expresses the real forces acting on it, force normal, force of gravity, force of friction. But for our calculations, it's very convenient to take the force normal and force of gravity and just look at the sum of those two and call that force parallel. Now that takes those two out of plane ones out and replaces them with one that's in plane. And now I have just a single one-dimensional vector problem where my force net equals force parallel minus force of friction. And so the reason why we introduce this force parallel is because it takes out then the force normal and force of gravity. It replaces those two with something then that gives us a one-dimensional problem. So let's try a couple of problems with these. So for the first one, we have a box with a mass of 30 kilograms placed on a ramp angled at 40 degrees from the horizontal. And we're looking at the acceleration for a frictionless case, and then if we have a coefficient of friction. So I'll just draw a quick free body diagram for these. So we'll have our ramp. This one's angled up at 40 degrees. Now the angle given is always from that horizontal, so that'll be this one down here. So I'll put the box then on the ramp. Now we have two forces acting on it if it's frictionless. We have the force normal pointing up and the force of gravity pointing down. But again, we don't want to use those forces because again, those are off axis there. And so we want everything along this single plane. And so what we're going to do is we're just going to use force parallel as pointing down the ramp. And that we know is in the same direction as my force net. So I have my force net equals force parallel. They're in the same direction. So force net equals force parallel. And then I can just put in my values. So force net is mass times acceleration. And force parallel, which we just derived, is mg sine theta. Now you could put in the mass, but you will see that if we divide both sides by m, those are actually going to cancel out. And so I could just solve for g sine theta for the frictionless case. If you put the masses in, that would be fine. You could put mg sine theta divided by m. You'll get the same answer. So we have g times sine of 40. And if we solve for that acceleration in that case, then we'll get 6.31 meters per second squared. Now, if we add friction to this problem, what we'll end up doing then is just adding one more force. And so if we add friction, we have our box again on the ramp, and it's the same angle. Now we're just going to have two forces acting on it. So we'll have our force parallel, which is pulling straight down. Again, remember force parallel is just the gravitational and normal forces. I will put a force of friction pulling backwards. And then presumably we're heading still down the ramp, so we'll have a net force then in this direction. So then we can do our net force equation. And so our net force is equal to force parallel minus force of friction. And so we're given a coefficient of friction, and so again we can find our acceleration. We're going to have mass times acceleration. My force parallel is going to be mg sine theta. And then minus force friction, which is mu mg cos theta. Now again, because I have an m in all three of my terms, it turns out the mass again doesn't matter. So when I divide out the m, as long as all three terms have an m, it'll cancel out. And so I can simplify this one a little bit to a equals g sine theta minus mu g cos theta. And at that point I can just put my numbers in. Again, you could have also left your masses in and had mg sine theta minus mu mg cos theta and divided the whole thing out by m. You'll end up with the same final answer. So here we have g times sine. We still have the same 40-degree angle there. So mg, or just g sine 40 minus, and then our coefficient of friction is given as 0.25 times g, which is the 9.81, and then times cosine of 40. We'll put that into our calculator again, and then we get 4.43. And we'll see that then friction, of course, is slowing it down a little bit, so we would expect a slightly smaller acceleration. But with that force parallel, we can solve them very easily as one-dimensional problems rather than dealing with a 2D problem with the force normal and force of gravity. That one then with static friction. So we have a 600-gram block that's placed on a board. On one end of that board is going to be lifted slowly up until the block starts to move. And so if you put a block on a board and you lift the end up, there will be some angles at which it's not going to start to slide. But as you bring that up so the board is more steeply inclined, eventually you'll get to a point where, of course, the block is going to move. And again, the greater the coefficient of friction, the longer it's going to take it to move, but eventually it should start sliding down the ramp at some point. The other thing to remember when we're looking for those coefficients of static friction, we're looking at it at the point just when it starts to move, and really what we're interested in is the point just before that. And so just like we did in the lab, where we pulled on the block until just the point where it started to move, and we used that to find that coefficient of static friction. Remember, we are looking at the point just before it starts to move. And so we're looking at an object that's not moving, and so as before, our static friction is going to be a net force equals 0, because we're looking at that point just before it starts to move. So if you look at our free body diagram for this, we have our ramp, and so at 20 degrees is when that started to move, and so 20 degrees is just the point where those two forces are going to be balanced. And the two forces we're looking at then is force parallel. Now again, that's not a real force. It is just the sum of the force normal and force of gravity, but we're going to treat it as the force pulling down the ramp. And that's going to be then an equal and opposite to this force friction, then that's going in the other direction. And it's equal and opposite, again, because we're looking at the point just before it starts moving, which is how we find the static friction. So our force net is just going to be equal to force parallel minus force of friction. And because our force net is equal to 0, we can say that force of friction must be equal then to force parallel. Force of friction on a ramp is going to be mu force normal, and not just on a ramp, that'll be true for all of them. Force parallel, of course, we have the mg sine theta. Now force normal on a ramp, and this will be a little bit different from the other ones then, is going to be that mg cosine theta. And so if you remember from previous there where we derived the force normal and force parallel from the triangle, we had that mg cos theta as our force normal. That's going to be important whenever you're doing friction forces on a ramp, because friction forces involve force normal, and force normal on a ramp is that mg cos theta. Force parallel, as before, is mg sine theta. And again, the mg cos theta for force normal, mg sine theta for force parallel, those are worth remembering because they show up in every one of the inclined plane questions that we'll be doing. So a couple things we can see canceling out right away. Our masses cancel out on either side. Now we are given the mass, so you could put that in and you get the same answer. Our g values are also going to cancel out on each side because they show up there. And so mu cos theta equals sine theta. So I can divide both sides by cos theta, and I get mu equals sine theta, which is 20 degrees, over cos theta, which is 20 degrees. And so we can take sine 20 over cos 20, and my mu value then, if I calculate that out, will be 0.364. Now, one kind of an aside here, and I'm not sure if you guys would have done this in Math 10 or not, but the sine over cosine, there is a trig identity where your tan function, so tan of an angle, is equal then to sine of the angle over cosine of the angle. So you could actually simplify this a little bit to mu equaling tan of theta. And if you do tan of 20, you'll see it works out to be the same 0.364 as sine 20 over cos 20. Now you don't necessarily need to remember that because again you can solve that using the sine 20 over cos 20, but you can, as it turns out, shorten this a little bit using then this identity. I think that might have come up in Math 10, but I'm not certain, but that is a shortcut you could do as well. So we can start to add other forces in here as well. And so we'll look at this one here. We have an 80 kilogram sled that's being pulled up a 30 degree incline. The coefficient of friction is given as 0.125, and so we're going to be looking for the force required for the constant velocity case and then with an acceleration. And so we'll start by just drawing the free body diagram for this one here. And so you have your angle of incline, and then we'll have then the object on there. Now we have a number of forces acting on here. Now one force that's always there with our inclined plane questions is this force parallel. So we'll put that force parallel in right away. Now the next one we're doing is we're pulling it up the incline, which means that we must have some force applied pulling in this direction. And so this one's pulling up the incline. Now we have a coefficient of friction. That means we also have friction forces there. Now remember that friction is always opposite the direction of motion. Now very often on a ramp question, because we very often deal with things sliding down the ramp, my friction force is pointing up. But that doesn't have to be the case. So make sure you're always watching where your friction force is. Because we're pulling it up the ramp, my friction force, which always has to be opposite the direction of motion, is going to have to be pulling then down the ramp. And my net force, because I'm moving up the ramp, is going to be then in this direction going up the ramp. So my force net and my force applied have to have the same sign, and my force parallel and force friction then will have the opposite sign. So when I do my net force equation, I'll end up with force applied minus force friction and force parallel. Again, force net and force applied will be in the same direction. Force parallel, force friction will be opposite in direction. Now, for the first case where I'm going with a constant velocity, my force net actually goes to 0. For the second case where I'm accelerating it, it'll be in that case there. So if we do A first, I will make this force net equal to 0. And so then we'll have 0 equaling force applied minus force parallel minus force of friction. Now we can move the force parallel to this side, the force of friction to this side, and then that'll give us force parallel plus force of friction will be equal then to that force applied. Now at that point we just need to put in our values, and so force parallel is going to be mg sine theta, and we have all of those numbers. And we'll add to that mu mg cos theta, and we have all of those values as well, and then we can very easily then solve for our force applied. So we'll have 80 times g times sine of 30, and then we'll add to that the 0.125 times 80 times g times cosine of 30, and that'll equal then our force applied. And so if we put all those values together, we'll get a force applied of 477 newtons. Now the next case, part B, where the sled is accelerated at a rate of 1.8 meters per second squared, will be pretty much identical with just one extra term for the force net. So I use the same diagram here. The only difference now is that my force net isn't going to go to 0. So when I do my net force equation, I get my force net equaling force applied. Now remember, those two have to be in the same direction because those are both going up, and then still minus force parallel, and then minus force of friction. So in this case, I'm still looking for then this force applied, but I'll end up with force net and then plus force applied and the force of friction then. So I'll have 3 terms instead of just 2. So if I move these over, I'll get force net plus force parallel plus force of friction equals force applied. So very similar to the other one with just one extra term. And so I'll have ma for the force net. I will have mg sine theta for force parallel, and then mu mg cos theta for that force of friction. And the sum of those then would be my force applied. So if we put our values in for there, we can solve for our force applied. So I'll have 80. Now our acceleration was given as 1.8 meters per second squared. So 80 times that will give me ma. I'll have 80 times g. The angle is still going to be 30 degrees. So 80g sine 30. We have 0.125 for our mu value, our coefficient of friction. 80 times g times cosine now of 30. And that all equals now a force applied. And because we're accelerating, we are going to expect a greater force applied than we had with the non-acceleration or the constant speed case. And we see if we put these in, we get 621 newtons. And so we have a higher value than the 477. But that is, of course, expected because we're now accelerating and not moving at a constant speed. And again, when you're doing inclined plane questions, make sure you have memorized the force normal. You'll need that mg cos theta whenever you're dealing with friction. That's going to replace the force normal in that friction equation. And we'll always have this force parallel, which is an easier way to deal with the force of gravity and the normal force.